Finally, we can move away from all this talk about water and fluids and pipes and pumps and start talking about electronics. The reason that I've been talking about hydraulic systems is because there is something called the hydraulic analogy, which is a very good mental model for trying to understand what's happening in electronic circuits. And it works by relating electronic components to an equivalent in a hydraulic system, which people may be more familiar with already. The idea is that the volume of fluid is analogous to the amount of charge that moves around a circuit. The flow rate of the fluid is analogous to current in an electronic circuit. Pressure is analogous to voltage, and a narrow pipe is analogous to a resistor. The one that isn't in this list is that a pump is analogous to a battery or a voltage source. I'll say a bit more about these electronic concepts and units now. Charge is measured in coulombs, and it can be thought of as a kind of volume of electric fluid. Current, measured in amps, can be thought of as the rate of flow of this electric fluid past any point in a circuit. 1 ampere, or 1 amp for short, is 1 coulomb per second. Voltage, analogous to pressure, is measured in volts. And if free to move, a charge will always try to get from an area of high voltage to an area of lower voltage in exactly the same way as, if free to move, a fluid will try to get from an area of high pressure to an area of low pressure. Resistance, measured in ohms, can be thought of as related to the narrowness of a pipe. The narrower the pipe, the higher its resistance in ohms. A high resistor resists the flow of electric charge in the same way that a narrow pipe resists the movement of fluid through it. The concepts of energy and power apply equally well to electronic circuits as they do to fluids. Work or energy is measured in joules. Power, which is the rate of doing work or the rate of acquiring energy, is measured in watts. 1 watt is 1 joule per second. Now, a volt is defined in terms of the amount of energy that it takes to move a coulomb of charge. If you're moving a coulomb of charge from 2 places in a circuit which are 1 volt apart in terms of their voltage, then you have to use 1 joule of energy to do it. Energy is therefore equal to the charge that's moved, often use Q to represent charge, multiplied by the voltage difference through which that charge has moved. If I just ask how much energy do I need to use per unit time, maybe per second, then energy per second, that's just the power, by definition of power, the rate of using energy per second, is the amount of charge per second. Well, the amount of charge per second, that by definition is the current. Current is defined as the charge flowing past a point in a circuit per second. Often use I to represent current, times V, the voltage. And I'm going to write that as delta V, just as a reminder that it's the difference in the voltages that's important. The current flowing from a voltage of, say, V1 to a voltage of V2, that would be associated with that amount of power. It's the difference in the voltages that's important. Finally, for this talk, Just note that 1 ampere of current flows through a 1 ohm resistor when 1 volt of potential difference is placed across it. This is the definition of an ohm. It's the resistance such that if there's 1 volt across it, 1 ampere of current will flow. And from that we can get the very famous equation, which I'll talk more about later, called Ohm's law. The current is equal to the potential difference across the resistor divided by the resistance of the resistor. And remember, a resistor works like a very narrow pipe. Okay, that is the basic idea behind the hydraulic analogy. In the next talk, I'll extend it to cover another type of component and also discuss the concept of ground.